Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo.
Okay, think I've got control back. So my name is Bill Hardy. I'm the CTO of TESCO, and I'm here to lead you through our discussion this morning on harmonics. What we're going to try to do today is answer a number of questions. What are harmonics? Where do they come from? Why are they important to us? And then how do we measure them? And so I've got a lot of content, and away we go. So harmonics in the presence of power systems really means that the voltage and current waveforms are distorted, and they deviate from a purely sinusoidal waveform. There are lots of ways that can happen, and so we'll talk about a lot of the different drivers for harmonic content. Really, any repetitive waveform, and ideally, our grid is 60 hertz and it's perfect sine waves, and we know none of that's really true. So harmonics affect power quality, and they're a relatively new phenomena that we worry about, but they've been around for a long, long time. Back in 1893, only 8 years after the first AC power plant was built, engineers started worrying about something that had to do with motor heating, and it turned out it was harmonics. And so the first time the word harmonic was used in the electric power industry goes way back to the beginning in 1894. So a perfect waveform looks like this, nice sine wave. And it has an equation that's the RMS voltage times the square root of 2 times cosine of omega 0. Omega 0 is the 60 hertz, and then possibly some phase shift. When we get harmonics, what happens is that we get frequencies that are multiples of 60 hertz, or at least we can analyze them as multiples of 60 hertz. And we represent those complex waveforms by the sum of a whole bunch of 60 hertz, 120 hertz, multiples of the 60 hertz fundamental waveform. So this complex signal, which is one of the ANSI new harmonic test signals, is made up of a primary 60 hertz fundamental waveform and a lot of sinusoidal waveforms at higher frequencies. Similarly, this pulse waveform, which is also one of the new ANSI test waveforms, is made up of a 60 hertz component plus a lot of components at higher frequencies. So from time to time, we're going to take a little aside and do a little background. It's not like we haven't understood this for a long time. Fourier, a French mathematician, back in 1827, published a series of papers, and he talked about a mathematical theorem, which is now called Fourier's theorem, or I'm sure you've heard about Fourier analysis, which is the way we measure waveforms these days. And it goes all the way back to the 1820s. Okay, so, Westinghouse and Edison had this big battle over whether AC or DC was the right way to go. And at the time, Westinghouse, with the help of Tesla, won that battle because it was easier to transmit power at high voltage and low current, and you had less losses. And the world was relatively simple. With only linear loads, and we'll talk about that in some detail a little bit later. You had sine waves, motors or capacitors shifted the sine wave, but it was still a sine wave. And so we had a simple world. The power triangle worked, and people didn't really worry very much, except in a few cases, about harmonics. Most loads didn't generate them. Okay? And that held true up until the 1960s. Most loads were either resistive loads or they were inductive loads, plain synchronous motors. Okay? So loads that contain resistors, inductors, or capacitors are called linear loads. And they're characterized by the fact that the current is proportional to the voltage, though it may be shifted in phase. Then John Bardeen and Walter Bacane and William Shockley invented the transistor. And with the transistor came the ability to have nonlinear loads. So loads where the current was no longer proportional to the voltage. And just as a sort of interesting aside, when I did my thesis work at Princeton and at the University of Illinois, at the time in low temperature physics, I had John Bardeen on both of my thesis committees, both at Princeton and at University of Illinois. And John had the reputation and was the most terrifying thesis committee interrogator that there was. He was an incredibly brilliant man, and he would sit there during your 3-hour oral presentation and say nothing until he uttered his first word, typically about 2 hours in, and then he would ask questions, but as soon as you showed that you could answer them, he'd say, "Thank you. Now the next question." And he would keep asking more and more and more difficult questions until you couldn't answer anymore. So that's my John Bardeen experience for you. Okay, so harmonic sources. There are all kinds of things that now generate harmonics. And they generate it either because they have diodes built into them, and so the current only flows part of the time, or more characteristically these days, they have switching power supplies built into them, and they cause significant distortion in our loads. So, this is just another reminder. Back yesterday, we had nice loads, resistors, and synchronous motors. Today, our motors are probably DC, or they have multipole variable speed controls. We've got CCF light bulbs. We've got LED light bulbs, microwave ovens, all kinds of TVs and screens and computers. If you want to see a really nasty load, look at the load for a call center where you've got nothing but hundreds of computers and screens. An example of what we're talking about, a CCFL light bulb has a current waveform that simply looks like a sharp peak with a trailing edge and generates harmonics out well past the 50th. We now have a lot of diode rectifier 6-phase and 12-phase variable speed motor controls. These generate really nasty waveforms that look like 2 pulses on each half phase. So in fact, here's one in the real world, and you can see that looks nothing like a sine wave. And here's a synthesized variable speed motor waveform, and it's one of the waveforms also that's used in the new ANSI standards. Here's a ferroresonant UPS power supply. And here's a power supply from a desktop PC. And more, these are the kinds of loads we're dealing with. So devices such as SCRs and triacs, FETs, diodes, all of the semiconductor devices which basically control our world today, these produce loads that are nonlinear, and one of the ways that we discuss and talk about and analyze these loads is through the use of harmonics. Okay, I see a question that's popped up. When I talk about ANSI waveforms, do you mean C1224? Well, some of these waveforms are in C1224, but no, I really mean C12.20, C12, the new C12.1 that's about to come out, C12.31, and C12.46. The compendium in C12.24 are a lot of waveforms that have been measured in the field. Most of them come from NRC Canada in a study they did about 20 years ago. The waveforms that I'm showing here are the ones that appear in the standard and are used for testing the harmonic performance of meters. And we'll talk about that a little bit more when we get further into the presentation. Whoops, gotta get back to the right screen. Okay, so why are they important? They're important because they cause problems, okay? One of the areas where they cause a lot of problems is in motors. They reduce the efficiency of the motors because they make it harder to magnetize the copper, the iron in the motor stator and rotor, and they cause eddy currents and hysteresis losses. If there are harmonics at particularly high frequencies, they can cause skin effects, and this reduces the actual ability of the copper in the motor to carry its rated currents. All of these losses end up as heat. and they produce stresses on the motor. They can degrade the winding insulation. They can cause greases and lubricants to lose their ability to lubricate. And depending on the level of harmonic content, they can cause, because of these overloads, nuisance tripping of thermal protection systems in the motor. They also have another effect, and that is they can cause arcing between the bearing raceway and journals or balls, which creates a rougher surface, which increases vibration and friction losses, and this can lead to the burnout and breakdown of bearings. If they're really high dV/dt kinds of harmonics, they can create notching and ringing type of harmonics that may appear in certain kinds of drives. They can cause partial discharge arcing, and again, degrade insulation, reduce the lifetime of the motor. Now, there's one more thing that I wanted to talk about, and that is if the harmonics are of what's called zero order, they can produce currents, high ground currents in the ground connections. And if they're of what's called negative order, which is the fifth, 11th, etc., they actually want to try to make the motor go backwards if it's a synchronous motor. And this causes vibration and additional stress in the process. Now, in transformer banks, we get many of the same kinds of losses that lead to overheating, that lead to insulation failures. Excuse me, I got one ahead of myself. Transformers, very similar to motors, you've got eddy currents, you've got hysteresis losses, you've got core saturation that reduces the efficiency of the transformer, and you've got copper losses, again, due to skin effects. Because of this, if a circuit has harmonics, it's going to have higher VA than its kilowatt ability to deliver energy that the customer is going to pay for. And this is going to mean that we have to overrate the transformer in order to supply the customer's load. The transformer life, because it's overheated, is going to be reduced. And again, they're going to be, especially if they're high frequency harmonics involved, there's going to be higher insulation stresses on many of the components in the transformer and associated with the transformer installation. There are a lot of the same issues in terms of insulation stress and other things in capacitors, but there's a unique problem in capacitors that can be extremely detrimental and destructive. And that is the issue of resonance phenomena. When a capacitor is paired with an inductor, it forms a resonant circuit. And if the frequency of the harmonic is such that it matches the frequency of the resonant circuit, then you're going to get oscillation, and this oscillation can grow until either the voltage or the current is extremely unstable. And so there are two kinds of resonance that can happen. One is series resonance, and in that case, the voltage can become much larger than the voltage of the applied harmonic, and particularly at higher frequencies, this can do considerable damage, not only to the capacitor bank, but to the equipment connected to that feeder. Parallel resonance causes the current to go into high amplitude oscillations. That can not only cause troubles with the capacitor bank, but it can also cause transformer failure and failure inside the customer's facility. So back to a little background. We saw that Fourier came up with the math to think about harmonics back in the 1820s. The first thing that really caused the problems were diodes. Before there was the transistor, there was the diode, and in the 1930s, we learned how to build relatively high current selenium diodes. Then in the so we learned how to build variable speed motor controllers, in a sense. Then 47, we got Bardeen and the transistor. In the 1960s, silicone diodes that could carry large currents became available. And then in 1964, Cooley and Tukey, Tukey a professor at Princeton, Cooley a programmer at IBM Watson Laboratory, developed the modern FFT. And the modern FFT is the basis of everything we do in harmonic analysis. And Tukey developed it as sort of a interesting side issue while he was trying to solve a problem in the space program. And he didn't think much about it, and he was convinced by a friend to enlist James Cooley at IBM to actually implement in code and test the algorithm. Now, their paper on the FFT was published the very next year in 1965, and it's considered one of the most important developments in modern applied mathematics. And all the modern instruments and electric motors use some variant of the FFT to analyze the harmonic content of signals. And I was very fortunate to actually work in 1966 for Tukey, and at the time I was an undergraduate. I knew nothing about FFTs, but he also was responsible for a lot of other mathematical inventions, and he was showing me how to solve a complex curve fitting problem for software that I was working on for Dickey and his group that discovered the 3-degree black body radiation from the Big Bang Theory. So I've been very fortunate to have personal contact with a lot of people who laid the groundwork for what we do today. So how do we measure harmonics today? Well, we do that by digitally sampling waveforms, and we convert them to a series of evenly spaced measured values. So here on the left side is a waveform, and I only sampled it 16 times per cycle. And you can see sort of what it looks like, but if I was trying to do an accurate measurement of it so I could calculate, for example, the power in it, that's not really good enough. So today, with the advent of high resolution, rapid conversion, analog to digital converters, a typical measurement would look something more like this. And this one on the right has 256 data points for a single cycle. And typically, this data is taken continuously, and fast Fourier transforms are used to convert the data into harmonics. So someone was asking earlier about the waveforms that we're looking at in most of these slides. These come from ANSI C12.20, 2015, where 6 tests for harmonic performance for meters were added. These waveforms are what we call pathological examples. And when C12.24 was originally put together as a compendium of waveforms and methods that were in practice for calculating VA, after analysis of all the different waveforms that were looked at, we were able to identify some particular characteristics that seem to make meters generate bad answers. And so this is the set of waveforms that were created to test meters for their ability to handle these pathological cases. So now we have C12.1 and C12.20 currently are in the process of being combined into a new standard, which will be C12.1 2021, we expect. It's currently in the balloting stage, and it combines the high accuracy standard C12.20 and the base standard C12.1 into a single standard. And these same exact tests that were in C12.20 are also found in the new combined C12.1. C12.46 is a newer generation standard intending to eventually supplant C12.1 and be more in line with all of the international standards. It contains the same tests that are in C12.20, but they've been extended to provide accuracy requirements over a broader set of conditions, and also to measure both watts and VA from these harmonic waveforms. And the actual definitions of VA and watts under these conditions are contained in, sorry, made a typo there, C12.31 which is also reaching its final stages. And so C12.31 and C12.46 should both come out this coming year at the same time. So, going to take a quick little look at what's in C12.31. So, in there is a definition of RMS voltage. So, first, there's a definition of a waveform, an arbitrary waveform, defined in terms of Fourier coefficients. So any repetitive waveform can be modeled in terms of its Fourier coefficients. And so if we think back to the basic definition for RMS, it's an integral. And an integral is a continuous function. But that's really not how we measure things today. Today, we measure things as discrete measurements like we talked about earlier. And so to measure RMS voltage, there are two different approaches that we can use. One is the classic summation replacement for a continuous integral. And if we do that carefully enough with points that are frequent enough, the answer that we get for the summation in the time domain and a, well, continuous integral are going to be the same. Similarly, we can do the same analysis in what's called the frequency domain. Same data goes into both, but rather than summing the actual data points, we do a Fourier analysis and we sum the squares of the Fourier coefficients for each harmonic. These two approaches will give exactly the same answers if we've sampled enough points and the waveform is repetitive. And in the frequency domain case, in the Fourier analysis case, if we've included enough terms in the analysis. There's similar definitions for the current. And for active power, again, we have the basic definition that we've had since the beginning of time, which is the integral of the instantaneous voltage times the instantaneous current. In the time domain, in the modern world, we replace that by a summation over all of the voltage and current data points that we take simultaneously. Or in the world of frequency domain, we're basically taking the dot product of the voltage and the current, summing over the Fourier coefficients, or in perhaps a more familiar notation for some of you, summing the voltage, the RMS, the voltage coefficient, the RMS voltage, the RMS current, times the cosine of the angle between them for each individual harmonic. Okay? And then when we get to the apparent power, here's where things get very interesting, because once you have harmonics, the power triangle breaks down. It simply doesn't work in the world of harmonics. So there has been a raging discussion for over a decade now about how should we measure apparent power, and how do we use it in metering? Because each different way that it's measured classically gives answers that we would all agree don't really make sense for what we usually think of as apparent power, because we use apparent power primarily to compute power factor. And power factor is primarily used to provide billing penalties for people who load the grid with harmonics that cause these losses and other problems that we talked about earlier. So we're coming to a point of closure, I think. Finally, we've agreed what's going to go in the standard. And like I said, I hope that we'll be able to get that out next year. COVID has been a real benefit in some areas for standard work and problems in others as we do everything virtually, like we are today. Okay, so how do we really do this? Well, there's a lot of modern test equipment that can measure harmonics in the field. And we're very proud at TESCO of our new CAT 6330, which is a meter site analyzer system that's, we think, is really neat. It's small, lightweight, and extremely powerful. Okay, so with the 6330, we can measure waveform. We can measure harmonics. And what we're about to do is see that real time. So here's a screen. It shows three phases. We've got nice sinusoidal waveforms for the voltage and the current. And that's the ideal situation that we really seldom encounter. Here's a really messed up world. I've brought up 3 different sets of ANSI waveforms, and as you can see, except for one voltage that I've left as a sine wave, it's a mess. Now, what we're going to do is we're going to look at a live demonstration of what the harmonics and the waveforms look like for a variety of different situations. So I'm sitting in my basement office at home, and the 6330 that we're looking at is connected to a 3050, which is playing the utility and load, sitting in the office in Bristol. And now we're going to look at various and sundry waveforms and what their harmonics look like. So here's the first set of waveforms that we're going to look at. We've got a nice sine wave for the voltage, but the current is really distorted. And so if I want to look at the harmonics for that waveform, well, as distorted, so here's the voltage, and you can see it's got a single 60 hertz fundamental component. If I switch over and look at that display in log mode, so that now we can see the higher order harmonics, you can see that there are a few at lower frequencies that are down in the 0.1% range, but most things are down in the 0.001% range. So I'm going to go back to linear, and I'm going to go and look at the associated current that we saw. And even so, here we are. We can see that the fundamental is only about 78% of the total, and we've got really strong fifth and seventh harmonics. We've also got some others in the situation, and I can also hide that first harmonic so that we can get a much better view of the smaller harmonics that are involved. Okay. I can look at the voltage and the current at the same time if I want to. And remember, even though you have a harmonic in the current, unless you see the same harmonic in the voltage, those harmonics are only going to contribute to the VA and not to the build power. So in a situation like this, we would have a case where the customer was generating harmonics that was causing us problems in our transformers and perhaps elsewhere. And we were having to oversize the transformers, yet unless he's billed on a power factor penalty or on VA, we won't get any compensation for that at all. Okay, so let me go now. I'm going to go through back to where I started. Okay, and we'll go back to the columns. Okay, so here's another one of our waveforms, and I can hop back to waveforms. Okay, and I'll go to phase B. So phase B has got a couple of interesting waveforms. The current waveform is the waveform that we talked about as basically a phase-fired waveform. This is when you control power to a device by literally turning off the current using a SCR or triac for part of the waveform. It's the way old-fashioned dimmers operated, and it's a way that a lot of controls for resistive loads that you want to vary operate. The other waveform is very similar to one that we looked at earlier, having to do with a variable speed drive. Now, I can look at the harmonic measurements of those. Okay, so the harmonics for the voltage really only have a couple of components, but one of those is the fifth, which is one of those negative sequence harmonics. The other is the seventh, and both of them cause serious problems in motors, and they're quite often generated by motor systems. Okay. I'll go down to the current harmonic. Now remember, this is the one for this waveform, which is again the 90 degrees phase fired waveform. And one of the things that's true about it is its harmonics go out to very high order. And the sharper that transition is, and the more ringing that's associated with it, the higher order these harmonics go to. So this kind of control used to be used in a lot of furnaces and other kinds of heavy industrial applications, and it can really cause problems in the transformer. Okay, and I want to do one more. Let's go back up here. Okay, so this is our pulse waveform, the typical waveform out of any switching power supply or even poorly constructed linear power supplies. You would be surprised how much of the world looks like this today. Going back to the harmonic analysis of that, up over there. Okay. So there's quite a bit of distortion in the voltage, more so than you might think. And this happens typically because the potential transformer, if you're operating a PT-based service, can't handle the crest factor of the current that's being drawn. And so you'll get a dip in the right at the peak of the voltage waveform. And okay, so I'm going to stop the live demo and go back to the slideshow now so that we can finish up and have some time for questions. And to do that, I'm going to skip past all of the images of waveforms and harmonic analysis in it, so that because we just did that, and it'll be in what's posted on the website for your future review. So, summary. Harmonics are created by nonlinear loads. They cause losses in the distribution system. They cause problems and failures in utility equipment, transformers, capacitor banks, and they cause the same sort of problems in your customers' equipment, in their motors, their electronics, their control system. They create metering problems and challenges, and not the least of which because our standards haven't caught up to the technology. So we're seeing different meters, and this was much more prevalent 10 years ago before we started working on this in the standards bodies, but we still have most of the meters that are deployed, which under harmonic conditions don't give the same answer for VA. or power factor. Okay. Because they damage equipment, harmonics have a significant economic effect on the things that we do. And the only real way to remove the economic effect is to remove the harmonics. And we have ways today to do that in many cases, but in others, we simply have to change the technology that we use if we want to make the loads better. So I ran across the other day a paper on the internet. It's probably the most complete in one place discussion of power system harmonics that I've seen. And so it's by Professor Matt Grady down at the University of Texas in Austin. I highly recommend it. Don't let the math discourage you. It's a very long paper. It's got tons of math in it. If you don't want to try to understand the math, just skip it. The words are worth the effort. So thank you all. And do we have any questions?
Hey, Bill, can you hear me now?
I can hear you now.
Yay!
Welcome back.
I fixed my technical difficulties. Thank you so much for taking over for me. And thank you everyone for joining us again for TESCO Tuesday. I don't know, Bill, if you have time afterward, if you'd want to continue some of that live demo, if anyone's interested to do that, I can certainly open that up. If anyone else has any questions that you would like to put into our chat, that would be fantastic. And if you want to move to the next slide, Bill, I'll tell everybody what's coming up the next few weeks. We will be off next week for Thanksgiving. I know this year's not the normal for everyone, so we do hope whatever you are doing for Thanksgiving, you're doing it safely and you enjoy it. We'll see you the following week on December 1st for complete site testing. And again, we'll be talking a little bit about our new 6330 meter site analyzer, but also how to do just regular complete site testing and what you guys should be looking for and all that. Following week, we will be doing electric vehicle trends and calibration of commercial chargers, and that's on December 8th. And following week on the 15th, we'll be doing streetlights and 5G metering and testing. And then we're going to take a break for the holidays, and we'll be sending you guys some information about spring sessions as well. And again, any questions you guys have, feel free to reach out to me at andrea.cook, K-O-C-H, at tescometering.com. You can feel free to check out our website, and you can go into our presentations, and you can view any previous presentation. You can view, we actually videotape them all now and put them up there as well. If you like to hear Bill give the presentation, you can certainly do that. You can share it with everyone. And can you go back a couple slides, Bill, to the link for that paper again, please? So
Sure.
Everybody can see that. And we'll put all this information online as well. And we'll let you guys hang on for a bit. And Bill, if you want to continue some of the live, we're getting a few questions here. Bill, can you read them? Can you see them at all? Or you want me to read them?
Hold on, I'm not seeing them. My camera disappeared. Let me get back. Okay. Yeah, and if you want to, Andrea, you can open up the audio and we can take some verbal questions as well. So let's see. Let me see.
So we have Aaron. I can unmute Aaron if you want to ask that.
Okay, hi, Aaron.
You should be able to see a mute on your end, Aaron, if you want to unmute yourself.
Hey, Bill, this is Aaron Snyder from Internet. How are you?
I'm good. Nice to talk to you again.
Yeah, thanks. So we were just wrapping up a project that dealt with technical and non-technical losses. And of course, under unaccounted for energy, one element of that, the distribution system, is, as you have covered very thoroughly, the way that there's a lot of harmonics in the distribution system. It causes impact on equipment, but as an economic impact, is there some way to measure or compute that lost potential revenue so that the utility might better understand how more comprehensive metering, or maybe moving to VA metering or some other type of program away from simple kilowatt hours, they could compute that potential economic benefit?
Well, there are two kinds of areas that get affected. So let's talk about the one that most people consider the most important, and that's basically system losses. So when you have a highly harmonic load, there is dramatically increased heat dissipation and loss in both your transformers and your lines. So what happens is most of the loss occurs in the power transformer that is the first one encountered before at the customer. And here it generates significant overheating. So you may have a customer that's only drawing 25 kilowatt load, and you may have served him with a 30 kVA pad mount transformer, but he may be drawing 100 kVA if he has a really harmonic load. And so the big initial cost there is that the size of the infrastructure that you have to install may have to be several times larger to serve a customer with a highly harmonic load than a customer with a more reasonable load. So that's the really big issue. The other issue is that you as the utility are paying for all that energy loss. You're not billing the customer, but back at the power station, you're generating that energy. And since back at the power station, it's almost certainly true that all of that wasted energy has been filtered out by the network. You're buying VA that's very close to kilowatts. And then you're allowing the customer to use kilowatts that are nowhere close to the VA because of the losses that he forces onto the system. So that's one of the reasons why there's an increasing push to use VA metering, or at least properly, consistently computed power factors based on consistently computed VA in order to have a billing methodology that better represents the impact of the harmonic customer on the utility. Sorry for being so long-winded there. Anyone else? Trent, I see you had a question. It's about one of the publication dates for one of the standards, but I don't know which one.
Okay, does anyone else have any questions? I don't see anything else in our chat. I don't know if you want to continue on with some of your live demos, Bill. If anybody wants to stay on, we do recognize you guys spent an hour with us. If you have to go, we understand. We'll continue recording, and then we can post this on our website, and we'll send it back out in our rewind email that we send you guys, so you can always catch us a little bit later if you have to go. If not, if you want to hang on, Bill, that's great with me.
Yeah, can you just unmute? I think you've got everybody muted. If you want to talk, just unmute yourselves.
Absolutely.
I think you should be able to do that.
I think they should too. If they have a question or you guys want to put it in the chat, I'll make sure we can unmute you.
Good morning, Bill and Andrea. This is Brian Cole from Ameren, Illinois. And I guess I'm curious, you gave a demo with the two units, and in our test lab, we have the TESCO MQB boards,
Right.
the new version. And I'm curious, can we simulate some of the harmonic conditions in those MQBs?
Yes, you can. You can generate any harmonic that you can write down the coefficients for. And all you have to do is create a simple CSV file in one of two formats and put that in your directory where the waveforms are stored in TMA, and you'll be able to use that on any of your systems. And if you want, just send me an email and I'll send you the details about how to do that.
I will do that.
I'll go ahead and put your email in the chat so everybody can see that, Bill.
Okay.
And actually, that might be a good topic for a future session, how to do that in the MQBs.
Yeah, I think that would be a good topic because they have a tremendous amount of capability that most people may not know about or use.
That's great. Thank you for that, Brian.
And Brian, they should have all of the ANSI waveforms built in. So if you come to TMA and go to the manual setup page or to the page for setting up sequences in the database, you can choose sinusoidal waveforms. As I said, there are two different harmonic formats. There's an amplitude and phase format, and there's a Fourier coefficient format. And you can, all the ANSI waveforms are predefined. So you can do exactly what I did, which was simply pick the waveforms that you want. And I picked all, ANSI ones. And then the system will generate those just by click of a button.
Thank you.
You're welcome. Anyone else have a question? Come on, guys. I know you got questions out there. You're just shy. So you can see, as I said, I'm sitting here at home. I've got full control of a 3050 that's in the office. And as you can see here are some other devices that are online in the office. And then I also have, as I said, full control over the 6330, which is in the office. And this is a live display. So if I come back over to my TMA, and let's see, hold on. And I come in and I change, let's see, that's phase C. I change the waveform that's in phase C. Lots of screens and lots of programs running. So I'm going to change the current waveform that's in phase C. And voila. So this is something that you can do with any 6330 or any of, with TMA, any of our test systems. You can control them from basically anywhere and get live feedback of what's going on. So if I come here, I can actually see what the voltages and currents are set at. Okay, one last call for questions. Let's see.
It looks like you got some coming in on the chat. Can you see them, Bill?
Yeah, okay, so do the harmonics generate more heat than a regular pure sine wave at the same RMS? And so if we're talking about in a transformer, the answer is yes. And it's because a transformer is not uniformly efficient as a function of frequency. So power transformers are designed to be as efficient as they can be at 60 hertz. But nominally, they don't have to be efficient at higher frequencies. And so they're designed using core materials that don't work all that well at higher frequencies. That has the advantage of blocking those harmonics from getting back on the network, but it has the disadvantage that it turns them into heat in that transformer. The same effects happen, by the way, in your CTs and PTs. CTs that are used for metering are typically optimized for 60 hertz. And so the harmonics that they transmit may not be exactly the same as the real harmonics in a system. So another question that just came in is it really possible that a home user can generate enough harmonics that it really affects his bill? Well, I'd like to tell you the tale of a mega mansion. So when I lived down in Tennessee, and when the economy was booming, people would move down and buy a lot on the lake, and they would build what we called mega mansions. These were, 10,000 square foot, palaces. And it was not infrequent for them to have 320 amp service, or even multiple services. And the local utility typically would put in one transformer, one pad mount for every 2, or in the beginning, every 4 of these establishments. Now, what would happen historically was a house was a mostly linear load and typically would have power factors around 0.95. But these houses had the latest and greatest of energy saving devices. Back then it was CCFL light bulbs, it was variable speed motors, it was fancy stoves and ovens and lots of TVs. The loads that came from these places turned out to be more like 60% power factor because of the highly harmonic nature of the loads. And so not only were they not getting billed, they were blowing up pad mounts. So yes, a house today, except for maybe having an older stove or older fans or electric heating, is predominantly not a unity power factor load at all. It can be quite bad. Okay, well, thank you all for joining us. I invite you back to join us again. And if you have any topics that you'd like to see us tackle, just give us a shout and we'll add them to the 2021 list of programs. So once again, thank you all very much, and we'll see you next week.
All right. Thank you, Bill. And thank you, everyone, for joining us today. We will see you in 2 weeks for the next TESCO Tuesday. Have a great week, everyone.
Bye-bye.